Hello, hello. Okay, yeah, then let's start. Hello, I'm Shintaro, a pre-doctoral appointee at Argonne National Lab and actually a PhD student at the University of Tokyo. I'm belonging to the Pavans group, developing runtime systems such as MPitch, OSHU MPI, and Argobots. Today's my talk is about our lightweight threading model and our threaded lightweight and our threaded library for OpenMP called Bolt. All right, outline of my talk. So Bolt is a lightweight OpenMP runtime system based on LLVM OpenMP. In our Bolt library, OpenMP threads and tasks are mapped to lightweight threads provided by Argobots. With Bolt, OpenMP threads and tasking are optimized. Specifically from the user perspective, these 2 points are important. First, OpenMP threads are very lightweight compared with the original LLVM OpenMP, so Bolt can efficiently handle nested power regions. Also, Bolt has higher interoperability with MPI in terms of MPI plus OpenMP task, but we don't talk about it in this talk. So this work is highly regarded by the HPC community, so this work won the Best Paper Award at PAC 19. And anyway, so today's presentation is about the efficient execution of nested power regions. Introduction. And as you know, multi-threading becomes more and more popular. And in HPC field, OpenMP is the most popular multi-threading model. As OpenMP becomes popular, not only the user programs, but also runtimes and libraries are paralyzed by OpenMP. As a result, the current situation unintentionally introduces nested parallelism existing in multiple software stacks. For example, users OpenMP parallel calls call an external function, which happens to be parallelized by OpenMP parallel region again. If OpenMP threads are closed every time, if OpenMP threads are created every time the control encounters parallel region, the growth of OpenMP thread count is exponential. For example, the OpenMP parallel 4 creates a parallel region. When spawn threads, then usually as many as number of cores. So then each thread calls a degen function, which internally creates a parallel region, for example. Then the total number of threads count becomes, in this case, 16. And if there's one more parallel region inside dgen, then it can be 64 more. So because the major OpenMP runtime system map OpenMP threads to kernel threads or P threads, it causes a severe oversubscription of threads and significantly degrades performance. Okay, so enabling nested parallel region can exponentially create threads and significantly degrades performance. The widely adopted option is disabling nested parallel regions. This is the default behavior of OpenMP runtime system. However, such a loss of parallelism can hurt the performance. A typical case is strong scaling on massively parallel machines. So as the number of cores per processor is increasing and also the node count is increasing, the auto-parallelism might not be enough to assign work to all the cores. The problem of nested parallel region has been known for 25 years. So right now, OpenMP disabled nested parallelism by default here recently, and this is the default OpenMP setting. And many programmers are actually unaware of potential loss of parallelism. Beyond this, we can find 2 directions to alleviate this issue. The first one is about OpenMP has several workarounds to solve this nested parallel region issue. However, this workaround is only very effective if users know and control all the parallelism in the program, including all the software stacks. In other words, this idea is not very effective if you don't know the inner parallelism. The second one is about using lightweight threads instead of OS level threads for OpenMP threads. There have been several proposals, but they do not perform very well if parallel regions are not nested, flat. And to make the matter worse, they are often slower than the state-of-the-art Intel or LLVM runtime systems. As a result, the rule of thumb is disabling nested parallelism, but as the software stacks get more and more complicated and multi-threading becomes more and more important, and the solution to utilize nested parallel regions is demanded. All right, so we tackle this nested parallel region issue by adopting the second option, with deep performance analysis and optimizations. Our Bolt runtime system is a lightweight user-level threading library based on LLVM OpenMP, which performs best for both flat and nested parallel regions. Okay, we'd first like to talk about the background of this work. As I explained, the nested parallel regions have been considered as a problem for decades. So since the major OP runtime systems map OMP threads to kernel threads, the OpenMP standard tries to solve this problem in several ways. And essentially, OS level threads are a little bit heavyweight. So the workarounds are trying to reduce the number of threads in total. For example, disabling nested power region, which is the default OpenMP behavior till recently, and all the nested parallelism is lost. And manual fine-grained setting, for example, by setting the number of threads per level or per region is another option. If users know everything, it might be the best solution. But it is very hard and maybe impractical to tweak parallelism at each level based on the available number of cores or inputs or some kind of like software configuration and like every other stuff. And the third option is limiting the total number of threads in the system, which can adversely serialize in power regions. There is another option, dynamic or automatic. The number of threads is automatically adjusted by the system, runtime system. But such an adaptive and dynamic technique sounds promising, but it won't work in practice because finally the runtime system doesn't know the parallelism in the program. Then using OMP tasks instead of OMP threads can reduce the oversubscription cost. Tasks can be implemented as a function pointer and its argument ultimately. So it's very lightweight. But unfortunately, most programs still use OMP threads, OMP power 4. And more importantly, tasks lack some features that threads have. For example, tasks do not support task-task dependency. Task-task synchronization, for example, task barrier, or TLS, or Affinity. So these workarounds do not, fundamentally solve the problem of nested power region. The root cause of this problem is using heavyweight OS level threads as OMP threads. Then how about using lightweight threads for OMP threads? Lightweight user level threads, ULTs, are often used to abstract lightweight fine-grained power units. Please look at the left figure, and OS level threads are fundamentally heavy because this thread kernel, interaction is very costly, and any context switching involves these heavy kernel operations. ULTs are implemented in user space. So they run on the traditional P threads in the figure in their general, OS level threads like this. But ULTs do not use OS scheduler for context switching. So every context switching is implemented in user space. And this can significantly reduce threading overheads. For example, one implementation of user level threads, Argobots, has 350 times smaller fork and join overheads than that of P threads. Then using user level threads can significantly improve performance. So we use LLVM OpenMP, one of the most efficient OpenMP runtime systems in the world. And for user level threads, we use our state-of-the-art user level threading library, Argobots, and replace the P thread layer with Argobots. This replacement is not technically hard, so it's very easy, just replace it. Then let us call this ULT version bolt baseline. So in bolt baseline, we create P threads as many as number of cores. And then each P thread runs a scheduler, and the schedulers schedule user level threads associated with OpenMP threads. Compared with the P thread version, even if we create OMP threads more than number of cores, the total number of P threads or OS level threads is the same. So there's least oversubscription cost. And does it perform very well? So we run this nested power microbenchmark on 56 core on Skylake. And this thread count of outer power region is changed, while the thread count of the inner power region is fixed to 28. Then this is faster is better, so lower is better. The figure shows that the bolt baseline, so without any optimization, is much faster than new OMP, GCC OpenMP. However, compared with the existing ULT-based runtime systems like MPC, OMPI, and OpenMP compatible OpenMP SS, the performance of the bolt baseline is not very good. Surprisingly, compared with well-tuned Intel and LLVM OpenMPs, both baselines about 7 times slower, even in the case of nested power regions. Okay, then why? So in this section, I'd like to explain why, and we will come up with some optimization for this. Just replacing OMP threads with user level threads does not perform very well. So to truly exploit flat and nested power regions, we found the necessity of several optimizations. First, solving scalability bottlenecks in LLVM OpenMP. Second, ULT-friendly affinity implementations. And third, efficient thread coordination algorithm. So look at the evaluation chart. So finally, performance will look like this. So using the same user level threading library, but more than 10 times faster than the baseline. Okay, so I'll explain optimizations one by one. The first one is resource management optimizations. We first found that in LLVM OpenMP, most threading resources like thread descriptors and team descriptors are protected by a single lock. and creating a large critical section on the fork join path. So we first divide a large critical section by creating more fine-grained locks per object to alleviate the contention. Furthermore, in OpenMP, power region is always created as a team, not multiple independent threads spawn and join. So using the team concept can improve resource management. So the team concept makes the team level data caching possible and which can efficiently access reused team data. This is called hot team in LLVM OpenMP. So in addition, we optimize the thread creation method. Previously, the master thread accessed the child thread sequentially on fork and join path, but divide and conquer thread creation is more efficient in terms of critical path. We know that overall, the overheads are negligible when you use OS level threads, but with lightweight threads, the bottlenecks become very significant. All right, so let's see the performance. This is a nested power benchmark, nested power region benchmark that has no computation. So efficient resource management significantly reduces overheads when many ULTs are created, while binary thread creation shortens the critical path when the parallelism is very limited. Okay, the previous optimizations are to fix the kind of artifacts of LLVM OpenMP runtime systems. In this section, we will focus on affinity, which is often ignored with user-level thread-based implementation. In general, thread affinity or thread binding is useful to improve locality. I'd like to explain how OpenMP affinity works. In OpenMP, place is a virtual location unit and can be specified via an environmental variable. So if we specify, for example, OMP places 0, 1, 2, 3, 4, 5, 6, 7 on an 8-core CPU, core 0, 1 becomes a place 0, core 2, 3 becomes place 1, 4, 5 place 2, and the last two cores become place 4, place 3. And when PROC bind is specified, the thread is bound to one of the place according to the PROC bind pattern. So with P threads, this affinity is set by CPU mask. However, ULTs do not have a CPU mask, so both baseline lacks the notion of affinity, which is still standard compliant because the effect of affinity is actually implementation defined in the specification. But this affinity setting given by users should be useful for both, not only to improve locality, but also to avoid contentions of thread queues by deterministic scheduling. Okay. Thanks to customizable scheduler provided by Argobots, both can implement place queues to implement affinity. The idea is very simple. So each schedulers become a virtual core or virtual processor and bound to a certain core. And then place queues corresponding to the places are created like this. So OpenMP threads running on top of user-level threads can be bound to a scheduler associated with a certain place. So this access control is done by a place queue. The ULT in the place queue can be taken only by the associated schedulers. For example, all right. So the schedulers, and this scheduler can take these user-level threads because it's in this place. However, you cannot take these user-level threads because this place, this core is not belonging to this place queue. This is okay because this is a shared queue. So it's like this. And actually, it works well and it's standard compliant, but from the performance perspective, it is not very optimal because OpenMP affinity setting is a little bit too deterministic. In OpenMP, once affinity is set in the parent power region, the child power region also needs to follow the parent place partitioning like this. So it is too restrictive to utilize random walk stealing in inner power region. So for example, in bold, it will be like this. So threads in the innermost power region cannot be scheduled by other schedulers out of the associated place. It's like this. It is forbidden. So one promising approach is deterministic work stealing, deterministic work sharing at the outermost power region to speed up the work distribution, but using random work stealing in the innermost power region for load balancing. And unfortunately, it is not possible in the current specification. So we suggest a new keyword, unset, to unset the affinity so that the child threads can be freed from the current affinity setting and run by any schedulers like this. Okay, so let's see the performance. So if you only set spread, the performance is sometimes faster, but not always better if the total number of threads is large because of the rigid affinity settings. If you set unset to the inner power region, it can overall achieve better performance. Okay, so in the following evaluation, we will set the affinity for bold. All right, right now, if nested, bold is most efficient. However, how about flat or single level parallelism? the performance of Bolt should be the same as others because, I mean, basically there's no point to use lightweight usable threads if there's no oversubscription. So performance should be the same. However, in reality, it is not the case. So Bolt is as slow as GCC OpenMP if we enable a special thread coordination optimization for p-thread-based systems. This optimization is specifically for flat parallelism. I said active to OMP weight policy for p-thread-based systems, and it can efficiently handle flat parallel regions. So what is a weight policy optimizations? OMP weight policy is a hint to indicate how threads wait for something. So let me explain active policy optimizations. So please look at the example code after this parallel region. So we can say that threads are waiting for next parallel region in the next iteration if it exists. And if the wait policy is active, these threads busy wait for the next parallel region after finishing the previous parallel region for a certain thread, certain period. And in this case, the synchronization becomes a simple busy wait flag checking. So like, these are actually checking only a flag. So no actual fork and join is needed. So of course, such a busy wait is catastrophic if there's oversubscription, but and also user needs to be responsible for it. But if there's no oversubscription, yes, this is more efficient. On the other hand, ULT-based systems always rely on user-level context switching, user-level fork and join. So after join, ULTs go back to schedulers and try to find the next part available work. The master thread will prepare new threads and they're picked up by schedulers like this, and then switch to threads and run computation. So since user-level scheduling is faster than OS-level threads, suspend and resume, suspend and resume is very fast, but still, compared with flag checking, this user-level threads operation is slower. All right, to solve this issue, let's implement active policy in Bolt. So like LLVM OpenMP. If active is set, each ULT busy waits for the next parallel region for a while. If not active is set, the passive case, the original fork join algorithm is used. Here's the performance. So if nested, passive is recommended to avoid wasting CPU resources by busy waiting, and Bolt is of course faster than GCC, ICC, and CLAN. But if not nested, active is recommended. So then Bolt is as fast as ICC and CLAN. It's a little bit faster, but it is not obvious like in this slide. So I know that the previous ULT-based systems did not implement active policies because usually ULT systems only focus on massive parallelism. Extremely speaking, they don't really look into the performance of flat parallelism. So their performance of flat parallel region is lower than those of widely used p-thread-based OpenMP systems. Okay, that's good. So in any case, Bolt performs best. However, as we have seen, the thread coordination optimization significantly affects the parallel region overheads. So if flat, active is better, while if nested, passive is better. So is there any way to transparently support both flat and nested parallelism? Okay, we first explain the idea. So if both active and passive cases, after the completion of OMP threads, child threads will enter the busy wait loop. In the case of active, if busy waits for a flag to restart the parallel region quickly. In the case of passive, it is in the busy loop to find the next available work. So if so, can we combine these two busy loops? Yes. So to support both flat and nested parallelism, we devised a new algorithm called hybrid, which performs flag check and queue check alternately in a busy loop. So in the case of flat parallelism, compared with active, it adds queue checking overheads, but still it can restart the parallel region without going back to the scheduler. In the case of nested parallel regions, compared with passive, it adds a flag check overheads, but still it can quickly find ready threads in their task queues. Okay, so let's see the performance. Here's the performance. So hybrid shows almost the same performance as flat active and nested passive. It means that we don't need to choose wait policy. Always set hybrid and performs best. This also improves performance if nested. So the left parallelism is limited, so left side parallelism is very limited, so it is not flat, but parallelism is not very abundant. Then hybrid policy can efficiently handle such a case and shows better performance than the passive implementation. All right, so summary of the talk, Bolt, design and implementation. So just replacing the threading layer is not enough, and we apply 3 kinds of optimizations to fully exploit nested parallelism without hurting the flat parallelism. Then it reduces overhead by 10 times. Okay, evaluation. And we have 2 microbenchmarks. Both of them require nested parallelism. The left case is balanced but insufficient parallelism. The inner loop only has 28 iterations, and the outer loop only has n iterations, where n is very small, while the server has 56 cores. So to use all cores, we need to parallelize both inner and like outer parallel regions. And then here's the performance. Now, as expected, Bolt always perform best, since now we can fully utilize lightweight usable threads, up to 4 times faster than Intel and LLVM OpenMP. The right microbenchmark has sufficient loop iterations, so in this case, both iteration counts are 56, but the computation size is unbalanced. To efficiently parallelize it, all the parallelism must be exploited. We changed alpha, we changed the degree of unbalancedness, it shows here. So with larger alpha, the computation becomes more unbalanced. And then this is the performance. So Bolt always performs best, up to 2 times faster than Intel and LLVM OpenMP. And I also implemented taskloop version of this microbenchmark and compare with those of GCC and ICC and Clown. So actually the OMP thread of Bolt is as fast as taskloop. So threads and tasks have different functionalities in OpenMP. Specifications, for example, thread support TLS, thread synchronization like barrier and affinity, while task support dependency-based synchronization. The result indicates that in terms of implementation, at least there is no significant overhead difference between OMP thread and OMP task. And this argument should be more like on the difference of functionalities. Okay, so let's see. Okay, very time. All right. Then if you use KIFMM, actually Bolt shows best performance. All right. So we can go to the summary. Okay. So basically, nested OMP parallel regions are commonly seen in the contemporary software stacks, and Bolt can solve the problem. I'd like to a little bit talk about the Bolt as a software. So this is developed as a kind of in the Argobots ecosystem. So if you use Bolt and if you use Argobots aware runtime systems, you can have a better interoperability in terms of correctness and performance. Also, Bolt is part of the ECP project. So I guess there are many talks about ECP SOLVE projects, about verification and verification suites, also compiler efforts, loop scheduling, but Bolt is working on runtime systems. So we are trying to improve the runtime part. All right, so you can download it from here or here. You can use SPAC as well. All right, and you can only change the library path and then you can use it. So you don't need to compile your program again. Okay, so you can just change LD pre-roll or LD library path. Then it works. Okay, features, and it supports most OMP 4.5 features. There are a few exceptions, OMPT and OMPD and task cancellations, but basically, Bolt supports most of the, significant features in OpenMP. All right, that's it. Thank you very much.